This PCB of the top-load washing machine is completely dead, and none of its functions are working at the moment. Someone has already tried to work on it, but it could not be fixed. You can see that work has already been done on all these points, because this box is packed inside with silicone, so someone has already removed it from here. Now, when such PCBs arrive, they should be recognized at first glance as to which PCB it is. Now look here, someone has already worked on this point, and someone has worked here as well. Similarly, this capacitor has been removed from here. Now, if we look at this capacitor, you can see that it is 16 volts and 2200 microfarad in capacity. Now, if you look at it here, you can see that it is slightly swollen on the top. It is only a little, not too much, but when such a situation occurs, this type of capacitor often completely or temporarily stops working. Now let's start repairing this PCB. The first thing to understand here is that this PCB is transformer-based. SMPS has not been used in it. So the first test, if the PCB is completely dead, is of the transformer. It is necessary to check it because if its high side is dead, then the low side will never be able to generate voltage. So first we check it. This blue connector here is our main supply connector. So we turn the PCB over and secure it here because it is falling. Okay, done. Now we will check the PCB in ohms mode. So the very first point we will check on the blue connector. So first we start checking from here. You can see that these 2 points are line and neutral connected here, and they directly go to the transformer points installed here on this PCB. So we check them here, and we will check in resistance mode. Let's see what ohms value is formed here. When the value is appearing here, you can see it is showing 2 kilo ohms, which is approximately fine. This means that its high side has no issue, because when electricity comes, this transformer will definitely work. Similarly, since the high side is completely okay, we will also check its low side. These 2 points here are the low side points, so we will check them as well in resistance mode. Here it is showing 7.7 or 7.6 ohms, which is completely okay according to the ratio. Since it has to convert into 12 volts, one side is 2 kilo ohms and the other side is 7.7, which is perfectly fine according to the ratio. First of all, we will understand this circuit, how this circuit is functioning here. Now, we will understand this classical power supply, how this classical power supply works. First of all, 220 volts comes here to the transformer, and then it is stepped down and converted into 12 volts. After that, here you can see 4 diodes are installed, which work as a bridge rectifier. So the bridge rectifier converts AC into DC. After this, you can see here a circuit is installed. This circuit generates the zero crossing. Through zero crossing, the microcontroller and this AIP1668 IC, when the zero crossing signal comes to this microcontroller and this IC, then only the microcontroller works. Otherwise, even if your transformer is fine, or even if the 7805 regulator is properly generating voltage, still, the microcontroller will not turn on in any case, because this zero crossing is the heartbeat of the microcontroller and this IC, and through this, the whole system runs. Now, I will explain to you how this function works. Here, DC is generated, and then you can see a capacitor is installed ahead of it. So this capacitor is doing the filtering work. After filtering, here a 30K resistor is installed, which is resistor number R18. Now what happens is that when 220 volts is converted into 12 volts, the frequency remains the same. There is no change in it. When 12 volts is generated from the transformer, it is still AC voltage here. So what happens is that these 12 volts directly come through this path, through this line, and reach here. Here you can find 2 resistors, as I already told you, R18 and R15. R18 is a 30 kilo ohms resistor, and it performs multiple tasks here. What happens is that the signal coming from here goes towards R15, and then it goes to the base. But I will explain this in more detail. Now, when this 12 volts AC is generated, what happens is that sometimes it goes into forward bias and sometimes into reverse bias, meaning sometimes it's negative and sometimes positive. Because of this, when voltage comes here on R15, when it's in positive, this transistor turns on. And when it turns on, the DC ground or negative point that is fixed here moves from emitter to collector. And this R18 resistor here works as a divider. This 30 kilo ohms resistor works in a way that here, the voltage can even go above 12 volts, right? So when the voltage goes higher than 12 volts, if the voltage becomes high here, then this transistor can get damaged. So this 30 kilo ohms resistor works here as a voltage divider or potential divider. So what it does is that if the voltage here becomes 15, 14, or 16, then at the base it keeps the voltage low, reduces it, which prevents the transistor from getting burnt. Now what happens next? I will make it clear. When this transistor turns on, then the emitter to collector ground signal through this path, you can see through R13, directly goes into the microcontroller and also into this display control IC. Now it happens that when this transistor turns on, it is also very important that it turns off. If it does not turn off, then the zero crossing will not work properly, because here 50 Hz per second signals are coming, and it converts these into 100 times signals, meaning when it turns on, one signal is generated, and when it turns off, another signal is generated. So the microcontroller should receive 100 signals per second at 50 Hz frequency. If it does not receive these 100 signals properly, then it will consider it wrong. A small 5 to 10% variation may be acceptable, but more than that, it cannot tolerate. Now what happens is that when this transistor turns on once, it is also very important that it turns off once. So how does it turn off, and how does the microcontroller receive the positive signal? Here comes the position of R12, which is a zero resistance link, and R11 is a resistor, which works as a pull-up resistor, with 5 volts DC attached to it. When ground comes here, these 5 volts move backward, but as soon as this transistor turns off, the signal goes through this path and comes back to 5 volts. When 5 volts comes here, it passes through R13 and then goes towards the microcontroller and this IC, and in this way the signal becomes complete. Now it is like this, that when this transistor turns on once, it is also very important to completely turn it off. If it does not turn off, that it will still create problems, and the signals will not come properly. Because if for any reason a floating ground is present here, then the microcontroller will not even understand whether the signal is positive or negative. That is why it is necessary to completely switch it off. Now, for turning it off, this ground also plays its role. So how does it work? This ground is coming here through these diodes, and it is also connected with this 30K resistor. Now what happens is that when the positive signal comes, this transistor turns on, but as soon as the negative signal comes, this ground also moves towards this side and works as a pull down through the 30K resistor. So if for any reason a floating positive voltage is present, it gets dumped to this side, and because of this dumping, the transistor turns completely off. And this whole process happens very fast, and it looks like nothing is happening, but in reality, everything is happening here. Apart from this, all the capacitors like C7, C11, C5, and C36 that are installed here are working as filtering components and are responsible for keeping the voltage stable. Then this 5-volt DC is connected to these triacs on the T1 pin. At this time, I've drawn only 2 triacs here, but normally in this PCB, there are 4 triacs, so I have not drawn all of them. I have only made 2 for reference. If this 5-volt DC is not present here, then the microcontroller will not properly understand whether these triacs are switching on and off correctly or not, because the microcontroller has the capability to pull and push current very effectively, meaning it can handle this line as positive and negative very well. And from this, it can judge whether they are working properly or not. Now, we supply electricity to this PCB and check why it is not working. For this, I turn the PCB. Now I switch on its electricity. After turning on the power, now let's check whether it is converting to 12 volts or not. At this moment, 13.95 volts are also coming here. These 3 points belong to the voltage regulator. Now, let's check this. And here 16.83 volts are reaching up to this point. After this, let's check what it is giving in the output. So let's connect it. Yes, absolutely. 5 volts are properly coming here. Now let's check its zero crossing. Now what we will do is place the black probe on ground, on neutral, and check the output of this transistor. So we check at this point, and here we are getting 2.68 volts, which is absolutely okay, because this meter does not have enough capacity to properly show the signals here. What it does is display the average voltage. Now I turn off the electricity. Now here, I made a small mistake. So you can see here, C36 is a capacitor installed, which is a 16 volt and 2200 microfarad capacitor. Now the capacitor I have is not 16 volts. So what I will do is, you can see this, I will install this 35 volt capacitor instead, because increasing the voltage rating here will not cause much problem. But if we reduce the microfarad value or make it too large, then an issue can occur. So that is why I will install a slightly bigger 35 volt capacitor, because here it is only for keeping things stable. for smoothing so that the DC voltage remains soft and stable. Now let's apply the power and check. It still did not turn on. Now there is a small issue here, which I will show you. Look here. When the machine runs, water or detergent comes into it, and because of the detergent, this point here, you can see, this entire area has become slightly disturbed. It looks like the copper here is no longer present, so this could be a problem causing disconnection. So what is the best way to fix this? For this, I have taken this sandpaper, and I will lightly clean this area. I will keep cleaning lightly, because if we check microscopically, there might be a disconnection. Although on the multimeter it is properly showing continuity, but when supply comes, it may still not work. So we will clean it properly, and after cleaning we will find the solution. If there is any disconnection somewhere, it will automatically get fixed. Now we will do soldering on all of these points. We will heat them and apply solder wire on them. So in this way, I have repaired it a little, and it has become somewhat better than before. Now the situation is such that the bridge rectifier and its voltage regulator are giving proper voltage. So we need to check these on the microcontroller. We will check a few points from which we can estimate whether this microcontroller is working properly or not. If there is any voltage difference at any point, then it might start working. And for example, if everything is correct, then it is also possible that this microcontroller itself is faulty. But until we test it, we will not be able to determine this. Now I will supply electricity to the system again. I applied power. Now what we will do is take the ground from here. You can see these 3 points on the right side, 1, 2, and 3. The center point here is ground, which is connected to pin number 32 of this microcontroller. So we will take ground from here. We place the black probe on ground, and then from here, if you see pin number 3, this pin, which is connected with capacitor C27, we check here. So here you can see 5.05 volts, stable voltage is coming. This means that the operating voltage required to run the microcontroller is reaching this point. So this gives us some level of confidence that the system may work properly. Now, the next point we need to check is whether the zero crossing voltage, which we checked earlier at that point, is reaching here or not. If for some reason there is any disconnection or issue along the path and it is not reaching here, then this microcontroller will not turn on. For this, pin number 13 of the microcontroller is assigned here, which receives the zero crossing voltage. So let's check here. I will take the ground from the same place where I connected earlier at pin number 32. Now this is pin number 8, then 9, 10, 11, 12, and this is pin number 13. So we will check here. At pin number 13, we are getting 2.67 volts. This means this point is also completely okay and there is no issue here. So the zero crossing is also reaching this point, which means its heartbeat is running. Now, the last thing we need to check in this is the oscillator, which is required to run this microcontroller. You can see these 3 points here, where the center one is pin number 32, and among the other two, one is input and the other is output, so we will check them. When we check, we will know which one is input and which one is output. So we connect the ground here, and this pin, you can see, this is pin number 30. We check at pin number 30, and here we are getting 2.336 DC volts. Now we check pin number 31, where the voltage is slightly lower. That will be the output. You can see here, the voltage is slightly lower, which means pin number 30 is input, and pin number 31 is output. But the voltage here is perfectly proper, which means the oscillator is also completely okay, and there is no issue in it. Now at the end, we will check whether this microcontroller has gone into reset phase or not. If you look at pin number 29 here, if reset voltage is not present at pin number 29, then it will go into reset mode and it will not turn on. But if voltage is present there, then it means we have to look for some other issue in it. So let's check it. From here we will count. This is pin number 32, then 30, 29, 28. So this point is also connected here. In the same way, you can see this pin is going around and coming to this capacitor. And along with it, there is a 10 kilo ohms resistor connected here. So the voltage is coming here. If 5 volts are not present here, then this issue can also occur. So what we do is take ground from here and check the voltage on it. You can see here a stable 5 volts are coming. This means its reset condition is also okay, meaning there should normally be no problem in it and it should turn on, but it is still not turning on. Now here, we have to go for the last option, because if this works, then this PCB will be okay. Otherwise, it will remain dead. So what I did is, you can see this 7-segment display, or maybe it is called something else as well, because these are 7 segments, and the rest are lights in it. So it might have some other name too. Anyway, I have opened it. You can see this is its whole system, and inside it the complete circuit is present. Now here we can very easily see that this oscillator is installed here, which is an 800 MHz oscillator. See, it is an 800 MHz oscillator. So now we only have the last chance, which is to replace it once. Because earlier in the video, I showed you that at this point someone had already worked on it, and these 2 points were shorted together. And this point was also not in good condition. It was disconnected. So I have soldered it, and now it is better. That is why we will replace this oscillator and see what difference it makes after changing it. So, we removed this one, and now I have another oscillator here. This is 800J, meaning an 800 MHz oscillator. I will cut it from here and install it in this. There is no input or output in it. You can place it anywhere. It automatically works as input and output. Now before attaching the display, we will give it power once and see if we hear any beep sound. I turned it on, but there is no sound from it yet. I'm not even sure which is the on-off button. Maybe this one or this one. Now I apply the power again and try turning it on. But it is not starting at all. So this means the microcontroller is completely unresponsive. There is no response coming from it at all. Because of this, we are forced to stop further work on this PCB, and it is impossible for us to repair it. Click on the left or right thumbnail to watch our next videos, and subscribe. Thank you.